Imagine standing right there at the ocean's edge. You hear that rhythmic crash of waves, feel the sand shifting under your feet. It feels so uh, permanent, almost timeless.
Right, but it's actually one of the most dynamic and rapidly changing places on Earth.
Exactly. So in this deep dive, we're really going to get into the world of shorelines, look at the powerful geological forces that are constantly sculpting these, unique interfaces between land, air, and sea.
From the tiniest water particles to the massive power of hurricanes.
Our mission, then, is to unpack the science behind all that change and explore its huge impact, not just on the planet, but on our lives, too. Get ready to understand why the shoreline really is Earth's restless edge.
It's an incredible place, this boundary. So much is always in flux. It's like a constant negotiation between these immense forces.
We often use terms like beach or coast pretty casually, don't we?
Yeah.
But geologically speaking, they mean specific things. Why is it important to understand those distinctions?
That's a great place to start, actually, because understanding the terms helps to understand the processes and, frankly, the vulnerability. So the shoreline itself, that's just the precise line where water meets land, and it moves constantly with the tides.
Okay, the literal water line.
Exactly. Then you step back a bit and you've got the shore. That's a broader area from the lowest tide mark right up to where the highest storm waves can reach inland.
Right, the whole splash zone, basically.
Sort of, yeah.
Yeah.
And then the coast goes even further inland as far as you find ocean-related features. It's all part of the bigger coastal zone, this whole interface where the land and ocean processes meet and interact.
A true meeting point.
Yeah.
And within that immediate shore area, are there like specific parts we should know?
Definitely. You can break it down. The foreshore is the part that's exposed when the tide is low, but underwater when it's high. Landward of that high tide line is the backshore, usually dry, only really gets wet during big storms. Then, looking out to sea from the low tide line, you hit the nearshore zone. That's where the waves start breaking. And beyond that is the offshore zone.
Got it. So each zone plays a role in how things change.
Absolutely. That constant modification is key. Waves, tides, currents, they never stop working.
Are there some really striking examples of how fast things can change? Or maybe places that resist change more?
Oh, for sure.
Yeah.
Look at Cape Cod in Massachusetts. You've got these cliffs left behind by glaciers, and they're eroding sometimes up to a meter, about 3 feet every single year. That's incredibly fast.
Wow, a meter a year.
Yeah, but then you go to, say, Point Reyes in California, where you have bedrock cliffs. They retreat much, much slower. So today's shoreline isn't just a snapshot you see. It reflects this really complex history. Think post-ice age sea level rise, landscapes already carved by rivers or glaciers, even volcanic activity or mountain building.
So every beach has this deep history embedded in it.
Exactly. Millennia worth of history.
And this is where it gets complicated for us, because something like half the world's population lives within, 100 kilometers or 60 miles of a coast?
Yeah.
That sets up a real conflict, doesn't it?
It absolutely does. Our presence creates this huge tension. We saw the devastation from Hurricane Sandy in New Jersey, for example. It really forces you to ask, are we building in the right places?
Because geologically, these features, especially beaches and barrier islands, are pretty fragile and temporary.
Extremely fragile in geological terms. They're not static. A beach is really just material in transit. It's an accumulation of sediment sand, maybe shells, sometimes even grains from basaltic lava on volcanic islands, whatever, is locally abundant. And it's constantly being moved around by the waves.
So less a permanent place, more like a sediment conveyor belt.
That's a great way to put it.
And you can see features on the beach itself, like berms, those flatter, sandy areas.
Right, the relatively flat platforms, often next to dunes or cliffs. And then there's the beach face, that wet, sloping surface running down from the berm to the actual shoreline. All of it is constantly being reshaped.
Okay, so if the shorelines are this restless edge, then the waves are the main engine driving that restlessness. It's kind of mind-blowing how wind can generate waves that carry storm energy thousands of kilometers away. How does that energy actually travel?
It's fascinating. The key thing is the water itself isn't traveling those huge distances. It's the energy moving through the water. Think about watching wind blow across a field of wheat.
Yeah. The wave moves across the field, but the wheat stalks just sway back and forth.
Exactly that analogy. The water particles are mostly moving in circles, passing the energy along, but they don't travel far with the wave itself.
That makes sense. So when we describe a wave, we're really measuring that traveling energy. We talk about its highest point, the crest, and its lowest point, the trough.
Mm-hmm. And the vertical distance between the crest and trough, that's the wave height.
Okay, how tall it is.
Right. And the horizontal distance from one crest to the next crest is the wavelength. And the time it takes for one wavelength to pass a fixed point, that's the wave period.
So height, length, and time. What determines how big these waves get?
Three main factors: wind speed, how fast it's blowing; the length of time the wind blows; and the fetch, that's the distance the wind travels across open water without obstruction.
The longer and stronger the wind blows over a bigger area, the bigger the waves.
Pretty much. Eventually you get what are called fully developed waves, where the energy they lose from breaking white caps equals the energy they gain from the wind. And even after the storm passes and the wind dies down, these waves can travel on as swells lower, longer waves, carrying that storm energy to faraway shores.
You mentioned the water particles moving in circles. That's the circular orbital motion, right?
Yep. Yes. And that circular motion gets smaller and smaller the deeper you go. There's a point at a depth equal to about half the wavelength called the wave base. Below that depth, the water movement is negligible. You wouldn't really feel the wave pass overhead if you were diving down there.
Okay, so the wave's influence only goes so deep.
Correct. And this is really important when waves approach the shore and enter shallower water, the surf zone.
This is where they start to feel bottom, as they say.
Exactly. When the water depth becomes less than the wave base, the wave starts to interact with the seafloor. This friction slows the wave down.
And what happens then?
The wavelength decreases, the waves get closer together, and the wave height increases. They get taller. Eventually, the wave becomes too steep to support itself, and the front collapses forward.
Yeah.
That's what creates the breaking wave, the surf.
And then the water rushes up the beach.
Right. That turbulent water rushing up the slope is called the swash, and the water flowing back down towards the surf zone is the backwash. It's this constant cycle right at the edge.
So we see how waves get their power and how they break. How do they actually do the work of erosion, especially during big storms?
Storms are when most of the erosional work happens. You've got the sheer wave impact and pressure. We're talking thousands of tons of water hitting the land. In winter Atlantic storms, the force can be like 10,000 kilograms per square meter.
Incredible force.
It is. Plus, air gets compressed into cracks in the rocks, which helps wedge them apart. And then there's abrasion.
Abrasion. Like sandpaper.
Kind of. It's the sawing and grinding action of the water when it's carrying sand and rock fragments. Think about those smooth, rounded pebbles you find on beaches.
Yeah, them tumbled around.
Exactly. The waves use those fragments like tools to grind away at the shore, often undercutting cliffs at their base.
So with all that wave energy hitting the beach, how does the sand itself move? Does it just get churned randomly, or are there patterns?
There are definitely patterns, and they often change with the seasons, or at least with the wave energy. During calmer periods, like maybe summer with lighter waves, the swash tends to soak into the beach more.
Because the beach isn't already saturated.
Right. So the backwash is weaker. The net result is that sand tends to move up the beach face, building up that flat berm area.
Making the beach wider, essentially.
Yes. But during high energy conditions, like winter storms, the beach is saturated. Less swash soaks in, so the backwash is much stronger. This erodes the berm and pulls sand down the beach face, moving it offshore. A wide summer beach can literally disappear in just a few hours during a big storm.
Wow. The beach itself really comes and goes. Now,
Yeah.
What about how waves bend when they approach the shore? That's wave refraction, isn't it? What effect does that have?
Wave refraction is crucial for shaping the coastline over time. Most waves don't come in perfectly straight, they approach at an angle. But as a wave enters shallower water, the part closest to shore feels bottom first and slows down.
While the part further out in deeper water keeps going faster.
Exactly. This difference in speed causes the wave crest to bend or refract, so it becomes more parallel to the shore contours.
Okay, so it tries to line itself up with the shore. What's the impact of that bending?
It concentrates the wave energy on the parts of the coast that stick out, the headlands, so more erosion happens there.
Yep.
But in the bays, the wave energy gets spread out, dispersed.
Leading to deposition in the base.
Precisely. So over long periods, wave refraction tends to straighten out an irregular coastline by eroding the headlands and filling in the bays.
Okay, so waves move sand up and down the beach, perpendicular to the shore. But what about the movement along the shore? That's longshore transport, right? The famous river of sand.
That's it. This river of sand moving parallel to the coast is driven by two main processes working together. First, there's beach drift.
Beach drift.
Yeah, imagine waves hitting the beach at an angle. The swash pushes sand grains up the beach face diagonally, but when the backwash flows back, gravity pulls the water and sand straight down the slope.
Ah, so it's a zigzag pattern along the beach.
Exactly. That zigzag movement alone can transport a lot of sand over time. The second process is the longshore current. This is a current that flows parallel to the shore, right within the surf zone. It's generated by those waves hitting the shore at an angle, and it moves suspended sand and gravel along with it.
So beach drift on the beach face, longshore current in the water.
And together they move huge amounts of sediment, often hundreds, maybe thousands of meters a day. On most U.S. coasts, the net direction is generally southward, but local conditions and seasons can definitely change that.
And sometimes that water moving alongshore needs to escape back out to sea, right? That leads to rip currents.
Yes, exactly. Most of the backwash flows back as sort of a sheet, but sometimes it gets concentrated into narrow, fast-moving flows heading straight offshore. These are rip currents, not rip tides. That's a common mistake.
And they can be really dangerous for swimmers. I think many of us have felt that sudden pull.
They absolutely can be. You can sometimes spot them because they interfere with the incoming waves, or you might see murky, sandy water being carried offshore.
What's the crucial safety tip if you get caught in one?
Don't panic, and don't try to swim directly against the current back to shore. You'll just exhaust yourself. The best strategy is to swim parallel to the shoreline. Rip currents are usually relatively narrow, so swim sideways until you're out of the strong pull, and then swim back towards the beach.
Good advice. Okay, so all these processes, erosion, transport, deposition, study, they create the features we see. What determines whether a coast ends up rugged and cliff-lined or sandy and low-lying?
A lot of factors play in. How much sediment is being supplied, say, from rivers? Is the land tectonically active, rising or sinking? What's the underlying topography and rock type? Prevailing winds, the shape of the coastline itself, it all matters.
We can group the results into erosional features and depositional features.
Broadly, yes. Erosional features are more common on high-energy, rugged coasts like parts of New England or the U.S. West Coast. Depositional features tend to form where wave energy is lower, allowing sediment to accumulate.
Let's talk erosion first. You see, waves cut cliffs, right?
Yeah.
Where the waves just chew away at the base of the land.
Correct. And as the cliff retreats, it leaves behind a relatively flat, bench-like surface at the base called a wave-cut platform. Sometimes, if the land is later uplifted tectonically, these platforms get raised above sea level, becoming marine terraces.
Like those step-like features you see along the California coast.
Exactly. The Palos Verdes Hills near LA have something like 7 distinct terraces, each marking an episode of uplift. It's like reading geological history right there on the landscape.
And what about smaller features carved out of headlands?
Waves are good at finding weaknesses. They might carve out sea caves and softer rock. If 2 caves erode back-to-back through a headland and meet, they form a sea arch.
And when the arch collapses,
We're left with an isolated pinnacle of rock standing offshore called a sea stack. Very dramatic features.
okay, so that's the carving. What about the building, the depositional features?
Right. Where sediment supply is plentiful and wave energy allows it to settle, you get features like spits. These are elongated ridges of sand that project out from the land into the mouth of an adjacent bay. Often, the end gets hooked landward by currents. Provincetown Spit on Cape Cod is a classic example.
And if a spit grows all the way across a bay.
It becomes a bay meth bar, basically sealing off the bay from the open ocean. Another interesting one is a tombolo that's a ridge of sand that connects an island to the mainland, or sometimes connects 2 islands.
But maybe the most significant depositional features, certainly for the U.S. East and Gulf coasts, are barrier islands.
Absolutely critical features. These are low, narrow ridges of sand running parallel to the coast but separated from the mainland by lagoons or marshes that can be anywhere from 3 to 30 kilometers or about 2 to 18 miles offshore.
And there are hundreds of them.
Nearly 300 along the Atlantic and Gulf coasts, stretching from Cape Cod all the way down to Padre Island in Texas. They typically have a wide beach facing the ocean, backed by dunes, and then the calmer lagoon behind them. How they originally formed is still debated. Maybe old spits, maybe sand piled up by storms, maybe drowned sand dunes from when sea level was lower.
So the big picture is that coastlines tend to evolve. Irregular shores get straightened out over time, headlands erode, bays fill in with spits, bars, and river sediment.
That's the general tendency, yes. A constant striving towards a smoother profile, driven by wave energy.
Now let's compare the U.S. coast, because geology makes a huge difference. The Pacific coast, that's an active plate margin, right?
It is. It's the leading edge of the North American plate. So you have active tectonic uplift, earthquakes, volcanoes. This results in a generally rugged coastline, often steep cliffs dropping right down to the sea, narrow continental shelf, fewer depositional features.
Contrast that with the Atlantic and Gulf coasts.
Totally different story. They're far from an active plate boundary, what we call a passive margin, tectonically much quieter. You tend to have broad, gently sloping coastal plains extending offshore as a wide continental shelf. This allows for features like those extensive barrier islands to form.
This difference relates to how we classify coasts based on sea level changes too, right? Emergent versus submergent.
Exactly. An emergent coast is one where the land has been uplifted relative to sea level, or sea level itself has fallen. So you might see those marine terraces we talked about, old wave-cut platforms now high and dry. Parts of coastal California show this, or areas like Hudson Bay still rebounding from the weight of Ice Age glaciers.
In a submergent coast.
That's where sea level has risen relative to the land, or the land has subsided. This floods former river valleys, creating irregular, indented coastlines with lots of estuaries.
So estuaries like Chesapeake Bay or Delaware Bay are prime examples of submergence.
Classic examples. The very picturesque, intricate coastline of Maine is another result of submergence flooding old glacial valleys.
Okay, let's go back to those barrier islands on the Atlantic and Gulf coasts. You mentioned the conflict with human development. Why are they so problematic to build on?
Because they're fundamentally dynamic systems. They're nature's shock absorbers for the mainland. They survive big storms not by standing firm, but by moving. Sand gets washed from the beach and dunes over the island and into the lagoon behind it, a process called overwash. The island essentially migrates landward over time.
Like a flexible reed bending in the wind rather than a rigid wall.
That's a perfect analogy, but humans tend to want permanence. We build houses, roads, hotels, and then when the island naturally wants to shift or overwash happens during a storm, we see it as destruction of property.
And the response is often to try and hold the sand in place with structures.
Often, yes. Which conflicts with the island's natural processes. Think about the Cape Hatteras Lighthouse in North Carolina. They spent decades and millions trying to protect it with various structures before finally admitting defeat and physically moving the entire lighthouse inland. It shows the challenge of trying to impose stability on such a dynamic environment.
Meanwhile, on the Pacific coast, they face a different issue related to human activity. Sediment starvation. What's going on there?
The problem there is often narrowing beaches, especially where they're backed by steep cliffs. A major cause is that many of the rivers that used to carry sand and gravel down from the mountains to nourish the beaches have been dammed.
Dams for water supply, flood control, irrigation.
Right. But those dams trap the sediment behind them. Look at the dams in the San Gabriel Mountains near Los Angeles. Like the Pacoima Dam, they prevent that natural sand replenishment from reaching the coast.
And the consequences?
Narrower beaches offer much less protection for the cliffs behind them during storms, so cliff erosion accelerates. Plus, development on top of the cliffs, things like lawn watering, septic systems, altered drainage, can increase runoff and destabilize the slopes, making them more prone to landslides or mass wasting.
So the erosion gets worse, and people might blame a single big storm.
When really it's often a combination of the underlying lack of sediment supply and the impacts of development, exacerbated by storms. And with sea level rise projected for the future, this problem is likely to get significantly worse on many parts of the Pacific coast.
Okay, we've talked about the everyday forces shaping coasts, but sometimes nature unleashes something far more intense. Let's talk about hurricanes.
The ultimate coastal hazard, really. These are intense tropical cyclones called hurricanes in our part of the world, typhoons in the western Pacific, cyclones in the Indian Ocean, some of the most destructive natural disasters, period.
What fuels them? Where does all that energy come from?
They're essentially giant heat engines. They run on the latent heat energy that's released when enormous quantities of warm, moist air rise and the water vapor condenses into clouds and rain.
So they need warm ocean water.
Absolutely, that's the fuel source. They typically form only over waters that are 27 degrees C, 80 degrees air, or warmer, usually down to a significant depth. This is why hurricane season is mainly in the late summer and early fall when ocean temperatures are highest.
And they don't form everywhere.
Right. They rarely form over the cooler waters of the South Atlantic or the eastern South Pacific, and they need the Coriolis effect, the spin caused by Earth's rotation, to get organized. That effect is too weak near the equator, so hurricanes don't form within about 5 degrees latitude of it.
Okay, warm water and spin. What's the structure like inside one of these monsters?
At the center, you have an area of intense low pressure. Air rushes inward towards that low, spiraling upwards violently due to the Coriolis effect. Think of an ice skater pulling their arms in to spin faster. This creates the powerful winds.
And the eye.
Right in the middle is the eye, a relatively calm, clear area, maybe 20 kilometers, 12.5 miles across. Inside the eye, air is actually sinking and warming, so winds drop and the rain stops. But surrounding the eye is the eye wall.
That's the dangerous part.
That's where the action is. It's a donut-shaped ring of towering cumulonimbus clouds with the most intense winds and heaviest rainfall in the entire storm.
Hurricanes are rated on the Saffir-Simpson scale, categories 1 to 5 based on wind speed. But what causes the most widespread and often deadliest destruction?
Hands down, it's the storm surge. This isn't just high waves, it's a dome of water, maybe 65 to 80 kilometers, 40-50 miles wide, that gets pushed to shore near where the eye makes landfall. Think Hurricane Katrina's impact on the Gulf Coast in 2005 or Hurricane Ike in 2008.
So it's like a bulge of the whole ocean surface moving inland.
Exactly. And then you have the normal wind-driven waves riding on top of that elevated water level. The height and impact of the surge are worse on coasts with shallow, gently sloping offshore profiles, and local features like bays or rivers can funnel the water and make it even higher and faster.
And there's a critical detail about where the surge is worst relative to the storm's path.
Yes, in the northern hemisphere, the surge is most intense on the right side of the eye, relative to the direction the storm is moving. That's because the storm's forward motion adds to the wind speed that's already blowing on shore in that quadrant.
Okay, storm surge is number one. What else?
Wind damage, of course. High winds turn debris into dangerous projectiles. Mobile homes are extremely vulnerable. Even well-built structures can suffer roof damage or failure. High-rise buildings can experience extreme winds on upper floors. Hurricane Andrew in 1992 caused catastrophic wind damage in South Florida.
In tornadoes, too.
Yes, surprisingly often. More than half of hurricanes that make landfall spawn tornadoes, which adds another layer of localized, intense destruction. The 2004 hurricane season was notorious for this.
And the third major impact.
Inland, flooding from the torrential rainfall. This can be a huge problem, affecting areas hundreds of kilometers inland long after the winds have died down. Hurricane Floyd in 1999 caused devastating flooding in North Carolina. Hurricane Camille in 1969, while devastating at landfall, actually caused some of its worst death tolls from flash flooding in the mountains of Virginia 2 days later.
It's terrifying. Thankfully, our ability to track these storms has improved dramatically. What are the key tools?
Satellites have been the biggest game changer. They allow us to see storms forming over the open ocean, estimate their intensity, track their movement. We can even spot features like hot towers, unusually tall clouds in the eye wall, which research suggests can indicate a storm is about to intensify rapidly, as was seen with Katrina.
And we still fly planes into them.
We do.
Mhm.
Aircraft reconnaissance missions fly right into the storm to take direct measurements of pressure, wind speed, temperature, and humidity, and pinpoint the exact center location. That data is critical for accurate forecasts.
What about when they get closer to land?
Then land-based Doppler radar takes over. It gives incredibly detailed information on the storm structure, wind fields, rainfall intensity, and short-term movement, allowing for specific warnings for coastal communities.
It's a huge difference from, say, the Galveston hurricane in 1900.
A world of difference. That storm killed around 8,000 people, largely because there was almost no warning. Today, thanks to these tools and improved communication, the death tolls from hurricanes in developed countries are generally much lower. Though tragically, property damage costs continue to soar because more and more valuable infrastructure is being built in vulnerable coastal areas.
Which brings us back to that question of what we do about coastal erosion and whisk. Yeah. We try to stabilize the shore. How does that usually work out?
Well, the traditional approach involves hard stabilization building structures, but they often cause unintended problems. For instance, jetties. These are usually built in pairs, extending out from the mouths of rivers or harbors.
To keep the channel from filling with sand, right?
Exactly. But they act like dams for the longshore transport. Sand piles up on the side, the current is coming from the upcurrent side, but the area just downcurrent gets starved of sand and erodes badly.
So you solve one problem and create another one next door.
Pretty much the story with many hard structures. Take groins. These are barriers built perpendicular to the beach, designed to trap sand moving along the shore and widen the beach in front of someone's property.
But they also starve the beach downstream.
Yes, so the neighbor downstream builds their own groin to capture sand, and then the next one does, and you end up with a whole field of groins, like you see along parts of the New Jersey shore. It doesn't really solve the overall erosion problem, just shifts it around.
What about structures parallel to the shore?
You have breakwaters, which are built offshore, parallel to the coast. They're meant to protect boat anchorages by creating a zone of calm water behind them, but that calm water allows sand to accumulate behind the breakwater, sometimes filling in the area you want it to protect, and again, causing erosion downstream. Santa Monica, California had this issue.
And the most direct approach, maybe. Building a wall right on the shoreline.
That's a seawall. It's designed to armor the coast and protect property directly behind it from wave attack. But seawalls are notorious for causing the beach in front of them to narrow and eventually disappear.
How does that happen?
They reflect wave energy straight back offshore, scouring the sand away from the base of the wall. Over time, the beach lowers and vanishes, leaving the seawall directly exposed to the full force of the waves, which often leads to its undermining and failure. Seabright, New Jersey, lost its once broad sandy beach because of seawall construction.
So the overall critique of hard stabilization is?
That it often benefits only a few property owners, degrades the natural beach environment enjoyed by the public, interferes with natural sand transport, and can be very costly to maintain, often just delaying the inevitable or making erosion worse elsewhere.
Are there better alternatives?
There are alternatives, though they have their own challenges. One is beach nourishment. This basically means artificially adding large quantities of sand to the beach system.
Like trucking it in or pumping it from offshore.
Exactly. The goal is to widen the beach, providing more protection and recreational space. It's been done extensively in places like Miami Beach and Virginia Beach.
But does it last?
That's the main drawback. It's not a permanent solution. The same coastal processes that caused the erosion in the first place will eventually remove the added sand. So it requires periodic, expensive renourishment. Virginia Beach, I think the source said, has been nourished over 50 times. And finding compatible sand the right size, shape, composition can also be difficult and ecologically disruptive.
What's the other main alternative?
Changing land use, or essentially relocation. This involves recognizing that some areas are just too hazardous for development. It means not rebuilding storm-damaged structures in high-risk zones, or proactively relocating buildings and infrastructure away from the eroding shoreline, allowing the coast to migrate naturally.
Like turning vulnerable areas into parks or buffer zones.
Yes. After Hurricane Sandy, some communities on Staten Island, New York, participated in buyout programs, turning flood-prone residential areas into open space to act as a natural buffer against future storms. It's similar to the approach sometimes taken in river floodplains.
But that sounds politically and emotionally difficult.
Extremely. It involves difficult choices about private property rights versus public safety and long-term resilience, especially in the face of rising sea levels. There's often intense conflict between homeowners wanting to protect or rebuild their property and planners or scientists advocating for strategic retreat or adaptation.
A huge ongoing challenge.
Okay,
let's shift gears one last time to another fundamental coastal process.
Yeah.
Tides, that daily rise and fall of the ocean surface. What's the driving force?
It's primarily gravity, specifically the gravitational pull of the moon, and to the lesser extent the sun on Earth's oceans.
The moon is the main player.
Yes, because it's so much closer than the sun. Gravity weakens with distance, so the moon pulls more strongly on the side of Earth facing it than on the center of Earth, and even less strongly on the far side.
Creating a bulge of water on the near side.
Right, but it also creates a bulge on the far side because the solid Earth is essentially pulled away from the water on that side, so you get these two opposing tidal bulges in the oceans.
And the Earth rotates underneath these bulges.
Exactly. As your location on Earth rotates through these two bulges each day, you typically experience 2 high tides and 2 low tides.
Why do the tides happen about 50 minutes later each day?
Because while the Earth is rotating, the moon is also revolving around the Earth in the same direction. It takes about 29 days for the moon to complete its orbit relative to the sun. So by the time the Earth has spun around once, 24 hours, The moon has moved a bit in its orbit, and the Earth has to rotate for about another 50 minutes to catch up to being directly under the moon again.
Okay, that makes sense. Now, how does the sun fit in? Its gravity matters too, right?
It does, although its tide generating effect is only about 46% as strong as the moon's because it's so much farther away. But the sun's influence becomes really important when we look at the monthly tidal cycle.
You mean spring tides and neap tides?
Exactly. Spring tides happen twice a month, near the new moon and the full moon. At these times, the Earth, moon, and sun are roughly aligned.
So their gravitational pulls add together.
Precisely. This creates higher high tides and lower low tides, a larger daily tidal range. It has nothing to do with the season spring, by the way. It just means the tides sort of spring up.
Okay. And neap tides.
Those happen twice a month, too, around the first and third quarter moons. Now, the sun and moon are pulling on Earth at roughly right angles to each other.
So their gravitational forces partially cancel each other out.
Yes, leading to weaker tidal bulges. You get lower high tides and higher low tides, a much smaller daily tidal range.
It's interesting that the tidal pattern isn't the same everywhere on Earth. Why the variations?
The shape of the coastline, the configuration of the ocean basins, water depth, all these factors influence how the tidal bulges move and interact with the land. This leads to three main patterns.
What are they?
Diurnal tides. Just one high tide and one low tide each tidal day. You see this in parts of the northern Gulf of Mexico. Then semidiurnal. Two high tides and two low tides per day, with the highs being roughly equal height and the lows roughly equal. That's typical for the U.S. Atlantic coast.
And third,
Mixed tides. Also two highs and two lows per day, but they are of unequal heights. This is common along the U.S. Pacific coast.
so the actual rhythm you experience depends a lot on where you are.
Absolutely. And associated with the vertical rise and fall of the tide, you also get horizontal movements of water called tidal currents.
The water flowing in and out.
Right. As the tide rises and moves towards the coast, the flow is called a flood current. As the tide falls and water moves seaward, it's an ebb current. In between flood and ebb, there are brief periods of slack water where the current is minimal or stops.
Do these currents do much work geologically?
They're very important in places like estuaries and tidal inlets. They scour channels and move sediment around, creating features like tidal flats, those muddy or sandy areas exposed at low tide, and tidal deltas, which are accumulations of sediment deposited by the currents, often just inside inlets on the landward side, flood deltas. But out in the open ocean, tidal currents are generally not major agents of large-scale erosion or deposition compared to waves.
We have covered a huge amount of ground, or maybe water today. We've seen how shorelines are this incredibly dynamic zone, constantly being shaped by wave energy, erosion, deposition, creating everything from massive cliffs and sea stacks to fragile barrier islands.
We explored the immense power of hurricanes, these ultimate coastal storms, and the much more subtle but relentless daily rhythm of the tides driven by the moon and sun.
And critically, we kept coming back to how our human decisions where we choose to build, how we try to stabilize these inherently unstable areas often clash head-on with these powerful natural processes.
Yeah, and understanding these forces isn't just, an academic exercise. It's absolutely essential for figuring out how we live on this planet, especially near these captivating but vulnerable landscapes.
It really leaves you thinking. As sea levels continue to change, as storms potentially become more intense, the question isn't if our shorelines will change. They absolutely will. The real question is how we will adapt.
Will we keep fighting losing battles with hard structures, or will we find more sustainable ways to coexist with this restless edge? Maybe sometimes that means stepping back and letting nature reclaim what was always hers to begin with. It's a profound challenge for the future.
A provocative thought to end on. Thank you so much for joining us on this deep dive into the dynamic world of shorelines. We really hope this journey through the geology has given you a clearer, more engaging understanding of these vital processes and why they matter so much.